Okay, I think we'll just get started. So thank you everybody for coming along today. We're in track 6. So normally we would have more of a geographical feel to it. We'd either be in a tiny room or kind of a big room or whatever it is. It sort of hasn't yet taken on its own feeling, room 6 yet, but I think we're sure we'll get there by the end of the day. We're here to talk about microservices. Well, I'm here to talk about microservices and specifically how we find microservice boundaries. And I'm really sharing some of the insights that I've had from doing research on a new book that I've been working on, and really looking at stuff in the past and trying to work out how that applies to how we think about microservice architectures today. And so that we're going to be talking about coupling, cohesion, information hiding in the context of microservices, and why these sort of quite old ideas are actually still really important for us to understand and take into account when it comes to thinking about how we find boundaries, both in our microservice architecture and maybe just even our modular monolithic architecture as well. My name is Sam Newman. I have written books before. I wrote this book, Building Microservices, that was released early 2015. I'm actually hard at work on the second edition of this book, which will be released in August of this year. My publisher has basically told me they're releasing whatever I've got, whether it's ready or not. So I've got to finish it, really. There's nothing like a hard deadline to drive some sort of urgency at the beginning of the year. You can get access to an early version of the second edition if you're interested. There's more information about that over my website. I also do sort of training, consultancy for clients all over the world who are sort of looking at microservices, considering if they're right for them, and for people who are kind of moving through those migrations. If you want to know more about that, again, information at my website. I will caution you that probably at least half of all the people who come to me and say, should I use microservices? I end up saying, no, you shouldn't, they're terrible. And won't somebody please think of the children? I also had a new book that came out at the end of last year, which was Monolith to Microservices. And this was a book looking at how you take an existing monolithic architecture and break that apart. Actually, no, that was the end of 2019 this came out. So this is about a year old now. I've just learned it is being translated into Japanese. So if you do speak Japanese, you can read this book in Japanese. More information about that again over there, lots of the resources. But we're here to talk about, more interesting things than my side projects. And that's to think about, well, why do we like microservices? What is it about microservices that makes this kind of architecture interesting? And the thing that I kind of come back to time and time and time again is this characteristic of independent deployability. This idea that I can make a change to a microservice, in this case, the accounts microservice. I can change that accounts microservice and I can deploy a brand new version of that microservice into a production environment without having to change any other part of my system. And it's this independent deployability that enables us to have like autonomous teams that can be more effective and efficient, working more in isolation, reducing coordination between teams. This also makes it much easier to achieve things like near zero or zero downtime deployments, which can be critical if you're running, say, 24/7 software, or if you just don't want to have to deploy software at the weekends and the evenings, you'd rather do it during the day. If you could achieve independent deployability at a logical level, it's much easier to put things into place to ensure that deployment of the software doesn't interrupt service. This idea of independent deployability, though, really hinges on one key idea, which is, in effect, maintaining some degree of backwards compatibility. So if I make a change to the accounts microservice here and deploy a new version of it, I need to make sure that I haven't broken my upstream consumer. So in this diagram, these arrows denote kind of dependency. So the arrow from the customer service to the accounts microservice is saying that this upstream consumer, the customer microservice, is making some use of the functionality exposed by the accounts microservice. So when I make a change to that accounts microservice, deploy a new version of it, I need to maintain compatibility with that upstream consumer. Because if I don't maintain compatibility, then I'm going to break my upstream consumer. And that's going to undermine my attempt to have independent deployability, because I deploy a new version of the accounts microservice and I break the system. And this is the key problem, right? If you're trying to implement a microservice architecture, is eliminating these accidental contract breakages becomes a key part of the sort of the early stage of your microservice build out. And I say this is something you have to kind of deal with fairly early on, because if you don't deal with this problem of breaking changes fairly early on, you don't have a later on to get to, right? You just give up on microservices because it ends up being too hard. So independent deployability requires a degree of stability in the interfaces that our microservice exposes. So maintaining a degree of backwards compatibility is really important to make independent deployability possible. And so here, when we do make changes to the contracts of our microservices, we're looking to expand them, add new things, add new functionality, add new optional, or removing fields, because that can end up breaking things. Now, I mentioned that I've been kind of looking at stuff from olden times, which in computer speak, olden times means, like before 2010. But if you go back a bit further than that, most of our programs were running on mainframes like this. This was if I think about 80s into mid 1990s even, the mainstay of a lot of sort of enterprise computing was programs running on mainframes. So companies would have a small number of very large, expensive mainframe-based machines, and our software would run on these. And through the 60s and 70s and 80s, these mainframes got more and more powerful. The programs that we wanted to run on these mainframes became increasingly more complicated. And so around the sort of in the mid 60s through the 70s, people started realizing as our programs were getting more powerful, because the underlying hardware was more powerful, as we were creating more and more sophisticated programs, we needed ways to make those programs more manageable. Your teams working on them got bigger. We had more people trying to collaborate on these things. And so how do we take these bigger programs and make them easier to work with and easier to develop? And this is really where sort of structured programming and the concept of modular software comes from. The idea being that rather than having one big giant program, we instead have that program consisting of multiple modules. These modules are things that we can work on in an independent fashion. So we have a section of people working on module A, a different set of people working on module C, a different set of people working on module B. So we get some sort of independent working. As long as the interfaces between those modules are the same, you can work in parallel to an extent. And then when it comes to assembling our program together, we pull those modules together, and that's our actual application deployment. It's actually kind of interesting to note that a lot of mainframes would actually allow you to hot swap these modules, which is actually not something that you can do properly on, say, the JVM or the CLR, which is kind of interesting. Modules like this also, of course, gave us the ability to reuse things between programs. And we use this idea quite a lot. If you think about reusing, open third-party code in our applications today, but that means, maybe module A is some common code that I'm reusing across multiple programs. The problem is this sort of concept of modular programming is quite a weak concept in most modern programming languages. The best we've got are things like namespaces and packages and sort of visibility levels and things like that. In the JVM ecosystem, they are doing some work to try and improve this concept of modularization. A lot of the work's been done around Jigsaw. But really, we don't really understand, I don't think, modular programming in the way that we maybe had to in the past. The closest we sort of get to is maybe thinking about reusing a third-party code via, gems, jar files, npms, NuGet, whatever it might be. So modular programming has been around for a very, very long time, and the thinking around how we make modular programs work has been around for a long period of time. It just seems that it's not necessarily knowledge that we necessarily take to heart very often. Now, of course, what happened was, mainframes were great, but we sort of the underlying infrastructure started to change. The economies of computing shifted. It became a lot more cost effective to go from having a small number of very large machines to shift instead to having a large number of, relatively speaking, small machines. So moving away from big mainframes to kind of modern server infrastructure. So certainly when I started in the mid-90s, sort of doing software development in anger, when I was actually getting paid for it, that was a time when some, company I was working at was just getting rid of their mid-range machines and replacing it with server infrastructure. Nowadays, of course, you wouldn't think anything of having hundreds of blades, but obviously most of your infrastructure now is virtualized. But this shift away from a small number of machines to lots of machines also shifted how we thought about building programs. Rather than having a single application that ran on a mainframe, maybe consisting of multiple modules, we now had lots of machines to run our software from. Service-oriented architecture emerged in a space where we were now trying to deal with what that meant. How do we take an application that now works across lots of different machines. And that's really what that service-oriented architecture is all about. Now, microservices, I think you could argue, is really a style of modular architecture. We're attempting to break the problem space down into modules. Those modules can be worked on independently. The main difference between, say, a Microsoft modular architecture and a traditional, say, mainframe or monolithic modular architecture is that the modules, rather than all now running in the same process space, now run on different computers. And, not just different virtual computers, but actually different computers. The communication between these modules are now being done via some form of network boundaries. This also, of course, gives us the easy ability to do independent deployability. Most modern monolithic modular applications do not allow for hot swapping of modules. The sort of Erlang Beam VM is a kind of an interesting outlier here. But the ability to dynamically change code inside, say, a Java process or a .NET process are extremely limited. So I would argue, though, that microservices, when they're done right, are ultimately a form of modular architecture, just one that happens to also bring along all the baggage associated with also being a distributed system. What this means, though, is that we can look at the work done around modular programming, structured programming more broadly, and apply some of those principles and thoughts into how we think about our own microservice architectures. One of the most sort of important concepts in modular programming is this idea of something called information hiding. The original article on the criteria to be used in decomposing systems into modules, it's a bit of a mouthful, by David Parnas, is probably the seminal paper in this space that really first introduced the concept of information hiding to the wider world. The paper was kind of originally published in 71 internally, released more widely in 72. David Parnas, who's still with us as far as I'm aware, was looking at what mechanism should we use for defining a module boundary to best allow us to kind of have that work done independently, have that to be allow us to sort of scale up our delivery efforts. And the concept of information hiding is what he came up with, which was this idea that we should hide as much information as possible. The idea being that if we hide the information within a module boundary, we never expose it, well, we can change it. Things that we don't share, we can change. Anything we share over a module boundary or a microservice boundary inherently becomes part of the contract that we expose to the rest of the world. And the bigger the contract that you have with other external microservices, the more challenges you're going to have in terms of maintaining backwards compatibility. Interestingly, back in 2016, Adrian Collier, who's used to be the CTO at SpringSource, and he basically kind of writes this great blog called The Morning Paper. So Adrian looks at computer science papers and kind of reinterprets them and sort of draws out the interesting insights. It can make a lot of computer science papers a lot more approachable as a result. He actually looked back at the various different papers by David Parnas and reinterpreted them in terms of, well, if I took out the word module, put in the word microservices, do all of these papers still make sense? And he sort of came up with the answer that, yeah, that kind of does. There's really interesting insights there. One of the nice things about this blog post is actually David Parnas himself found it subsequently and commented on it, sort of reinforcing some of Adrian's thoughts. So information hiding, well, let's look at this in practice. What do we mean by information hiding? Well, let's look at an example of a microservice where we're not hiding really any information. So here I've got my accounts microservice, and these little blue dots represent kind of the internal implementation, the methods, the objects that I might have internally. And I've got data that I'm storing in a database. And I've got an external consumer, right? Here I've got the shipping microservice, and I'm allowing that shipping microservice to reach directly into my internal implementation detail, right? And the problem is if I change that internal implementation detail, I break compatibility with that external party. So what we want to do instead is to hide those secrets. So what I want to do is be really explicit about what functionality is shared and what functionality is hidden. So in this example here, I've decided to hide everything in that green box. So everything inside that green box, all of that code, all those objects, the data, the way I store data, that cannot be accessed by anybody outside of this microservice boundary. Nobody can see it. No one can touch it. The only part of my microservice that I expose is in that explicit shared world. And this being explicit about what I share and being really limited or parsimonious in what I share is the kind of the core idea of information hiding. By being explicit about what I share, I'm helping not only the consumer, in this case, the shipping microservice, know exactly what it is that they can make use of, but I'm also being explicit to the developer who's working on the accounts microservice in terms of helping them understand what can change safely and what can't change safely. As a developer working on a microservice, it's really important that you have confidence that when you make a change, you're not going to break the system. And if you can be really clear to a developer and say, look, anything you change in this world, that's safe. You can change whenever you want in here and it won't affect anybody else. But when you go into this part of your code base, anything you change here could cause other issues. And now, therefore, you need to apply a high degree of care and do due diligence. And also, this is maybe where you can focus more of your testing efforts because the implications of getting this wrong are kind of much more significant. So information hiding is about reducing the size of the contract, simplifying backwards compatibility, making it easier to maintain compatibility as you change. It's about making it easier for a developer to make changes with confidence as well. And so this is just about being explicit, really. This is the prime reason why we don't like directly sharing databases. When you directly share a database to an outside party, well, you're kind of opening up a huge amount of your internal implementation details. There are other challenges as well associated that we'll come to later. A really common problem I find with people, again, this is an early stage problem with microservices, is they have this issue of accidental breakage. And that's because it's not always explicit or clear that a change they're making may actually end up affecting the external API. So here's an example, a little snippet of code, right? Here's a customer class, and we've got fields in this customer class here. And it's quite a common way. So say I needed to expose that customer over, say, an API boundary. A very kind of simple way of doing this would be to use some kind of, they say, an introspection-based serializer. So an introspection-based serializer is something that will look at a data structure, it will walk the fields of that data structure and convert it into some kind of serializable form. So in this case here, I could automatically generate a JSON payload from that just by walking the fields. So if I change that code, it's going to change the JSON that I'm exporting. So here we can see that I've got an age, right? So that's one of the fields I'm storing associated with the customer is the age. And we can see here that the age comes out in that JSON payload. Now, as a developer, I might go and look at that class and think, hang on a minute, storing the age of a customer as an integer like this doesn't seem to make any sense because, well, it could open ourselves to problems. Because if I load the data out of the database just before midnight and the next day their age changes because that's their birthday, well, then this age is now incorrect. So it might make more sense for me instead to store their date of birth. And then I could generate the age using code, and the age would then always be correct given a point of time. And that looks like quite an innocent change until you realize, of course, that that's now going to change the JSON that is exposed over an API boundary. So if you're going to do things like this, if you're going to auto-generate serialized payloads like this code effectively becomes part of your shared world. This stuff is no longer hidden. You also therefore need to make it very explicit to a developer as to what's going on. An example of how you could be very explicit here would be to do something like putting annotations on these fields to make it very clear they are being externally serialized. And then hopefully at the very least, a developer making that change should be able to see the annotation and realize, hang on, this might change the external contract. Another way you can handle this is to have sort of explicit data transfer objects. The idea being here is that you say, I've got my internal representations and my external representations, and I'm going to create an object, a data transfer object that's going to represent the external view. And so I might take my external version like that and then have a way of building a customer DTO. So in this example here, I would have to update the code that creates that customer DTO to kind of create that age based on that date of birth. And then if I'm always serializing the customer DTO and I maintain stability of that, that can help in terms of not making backwards incompatible changes. So this is all good in terms of being maybe more explicit and helping us avoid making breaking changes, but it would also be good if we could have things that catch us if we did make a breaking change. What we want to be ideally is a bit more explicit about the interactions between things, and explicit in a way that means that we could verify programmatically if we've broken an external party. Now, of course, we get this a lot of the time as a modular programming when we're working, say, in a modular monolith in say, a statically typed language. So if you're creating a modular monolith, say, using C#, if you try calling a method that's no longer there, the compiler breaks, right? You get that fast feedback straight away. You know that you've made an API change, which is breaking, right? Your code will not compile. So that's a lot easier. Dynamically typed language is a bit of a different issue. But it'd be nice, though, for a microservices world, if we could have something like the compiler that goes, hang on a minute, you're calling something that doesn't exist anymore. This could be an issue. So being explicit here is really nice. So if we could have an explicit understanding of the contract we expose, and more to the point, if we could have an explicit understanding about what our upstream consumers expect of us. So in this case here, I'd want to know what module B wants to use of me, and therefore I make sure I maintain their expectations. This will make it much easier for us to understand what we can change and what we can't. And this is one area where I think schemas are hugely underrated. So back into the late 90s, into the 2000s, the main communication protocol that was used in software service-oriented architectures was SOAP. And we got, and SOAP really has died a death for good reasons. It's kind of pretty heavyweight, right? The problem is when we got rid of SOAP, we also kind of all seemed to reject every idea that SOAP had as well. I mean, SOAP made use of an explicit schema, the WSDL format. It wasn't a particularly good schema format, in my opinion, but it was a schema format, and we seem to have rejected all of those concepts. Most people now are effectively sending untyped JSON over HTTP and pretending that it's REST. REST, by the way, doesn't say you can't do schemas. You absolutely can do schemas with REST. It's that people choose not to. Schemas are fantastic for helping catch up mistakes. If you are just sending plain old JSON over HTTP, you can make use of JSON schema. If you're making use of something like protocol buffers, you have to have a schema to define your serialization format. Why are schemas useful? Well, firstly, schemas are explicit. Secondly, they can allow for code generation. And thirdly, you can programmatically compare schema versions to detect backwards incompatible changes. There are programs that exist that will compare JSON schema versions and tell you if you've made a backwards incompatible change. I can do the same thing for Protolog, using Protolog for protocol buffer definitions. I could use the Kafka schema registry that will actually handle protobuffer, JSON, and Avro compatibility checking. If I'm using the Open API specification, I can compare two different versions of my Open API specification and say if one is backwards compatible or not. Why is that useful? You stick that in your CI build. You've made a change to your microservice. You've changed the interface. You've changed the schema in some way, shape, or form. Your CI build can say, hang on a minute, this is a backwards incompatible change. You could fail the build there and then. You never even try and deploy that breaking change. So information hiding, being explicit is useful anyway. By being explicit, schemas can really help us be explicit. By having schemas, we get this ability to programmatically verify whether or not backwards compatible changes have been made. Now, I need to be very clear, schemas only help you so far. They help you with structural breakages in contracts. So I could pick up things like, okay, a method that was there before is no longer there, or you've added a new non-nullable, a required parameter effectively to an existing method, as simple examples. That doesn't help you with semantic breakages in behavior. And that is where you would need testing. Now, if you have explicit schemas, you can focus any of your testing efforts, for example, using something like consumer-driven contracts, just on semantic breakages. But if you don't have an explicit schema, then you are forced to put a lot more testing around just what should really be the low-hanging fruit. This is kind of, analogous to me for when I'm doing dynamic typing, right? I really like dynamically typed languages. I use them a lot, but I accept that some of my tests are there to pick up things that would otherwise be picked up by a compiler in a statically typed language. And that's an acceptable trade-off for a dynamically typed language, in my opinion. I'm not sure it's an acceptable trade-off for the services architecture. So I actually really like having explicit schemas. And the key thing is here, I'm not saying it's not about schemas versus schema-less. It's about an explicit schema. Even if you don't have an explicit schema, you do have a schema, because your consumers have expectations about the structure of the data they're going to receive. They have expectations about the names of fields and what those fields contain. And that exists whether you have an explicit schema or not. If you don't have an explicit schema, it just comes down to guesswork, just trying to work out what it is that people want. So that's the difference, right? Now, moving on from information hiding, we talk more broadly about other concepts in this space of sort of modular programming. We can think of some stuff that's come out of the world of structured programming. I like flashing up copies of books like this that you can no longer get easily because they're very expensive online, disturbingly expensive, in fact. I was trying to track down a copy of Structured Design by Jordan and Constantine, and it was like 90 quid on Amazon. I would normally, in the normal times, I'd go to the library at the Canterbury University up the road here, but I'm not allowed to. So I had to make do with Kevin Henley sending me PDFs, photographs of the book. But anyways, loads of great stuff that comes out of this space. And, you know, a couple of terms that we've kind of heard before in the scope of microservices come from the world of structured programming. And these are two important terms to us, which are coupling and cohesion. And we typically talk about these concepts at a code level or a service architecture level in terms of the desirable properties that we want from these. And specifically, we talk about the fact that we want low or loose coupling, and then we want high or strong cohesion. And ideally, this is what we want: low coupling, strong cohesion. What do these terms mean? Well, there are different definitions and more specific definitions of these terms in the context of code. I tend to use slight variations of these terms for the service as well, because the services wasn't quite mapped to the code world. But fundamentally, when I think about cohesion, I'm thinking about the code that changes together, stays together. So if I think about an example, services architecture, where we're seeing weak cohesion, you know, I might think of a sort of layered architecture where the functionality that I'm trying to change is actually spread across the system. You know, if you find yourself constantly having to make a change in 4 or 5 different places, that's a sign you've often got weak cohesion. Distributed monoliths tend to have this property. Layered architectures often have this property. So, you know, if I want to change the logic of how invoicing is, you know, invoicing approval is done, I have to change like 5 or 6 different parts of my code base and different services and organize different deployments around that. Beyond the fact that the work to make those changes is much more increased and more error prone, it's also just a lot more hassle in terms of rolling those changes out. So systems have weak cohesion, tend to have higher maintenance costs and actually more bugs associated with that as well. So we don't like this. Ideally, I'd like to be able to make my change in one place and one place only and move on from that. The traditional kind of 3-tiered architectures really suffer from this because if you think about those sort of presentation, business data access type layered systems, they're really focused on collecting code together that has similar technical functionality rather than focusing on how we actually make changes in the real world, where we would quite often want to cut through those layers. Now, coupling is a degree to which changing one thing requires a change in another thing. And we'll talk about in a microservice architecture, we can see different types of coupling. Now, you might have heard of a thing called Constantines Law, which really kind of links these two ideas together. And actually, I think in a common sense way, it makes sense. So Constantines Law states that a structure is stable if the cohesion is strong and the coupling is low. Now, we would like a stable structure with our microservice architectures because we want stable boundaries. Now, how are these two things linked? Well, if my cohesion is weak, then I'm going to have to change lots of things to make a change to my software. If I'm having to change lots of things, then that would also imply those things are tightly coupled because I'm having to change all these things together. So you kind of see how these things are related. So if you actually improve the cohesion of your software, you will tend to also decrease the coupling. And we want decreased coupling because we want independent deployability. So these kind of ideas are related. So if you improve the cohesion of your system, you will likely also improve the coupling as well. And if you want to improve how loosely coupled your system is, you will actually end up improving the cohesion as well. These two things are inextricably linked. Now, when it does come to coupling, you know, there are different types of coupling out there. I'm not talking about temporal coupling or kind of runtime coupling really here. I'm talking kind of here about coupling in terms of one thing depending on another in terms of the functionality that it makes use of. There is an extent to which there will always be some coupling in a microservice architecture. Microservices fundamentally exist to be called or be made use of by other microservices. So there is an extent to which there is an inescapable degree of coupling. What we're trying to do, though, is minimize it and avoid the more egregious forms of coupling. So I'm just going to look at 3 different types of coupling that you might see in a microservice architecture. And there are others, but these are kind of just 3 I want to highlight for this talk. And we're going to look at domain coupling, common coupling, and content coupling. And what we're going to see is as we go kind of from left to right, these forms of coupling get worse. And so when you encounter the kind of coupling that happens more towards the end of this spectrum, you're going to want to put things into place that sort of pulls you back towards the left, if that makes sense. Domain coupling is this is the kind of coupling you're going to always see a little bit of. And that's just really the idea that one microservice is coupled to the domain functionality exposed by another microservice. If you're a REST head or a RESTifarian, as some people call themselves, who really like REST, you know all about the domain application protocol. This is effectively saying you have a domain application protocol. So in this example here, I've got an order processor microservice, and that has interactions with 2 other microservices. We've got the warehouse and the payment. So the order process here goes to the warehouse microservice, and it makes use of the ability to reserve stock. And the payment microservice, we use that to be able to take payment. Now, the payment microservice is where all the logic and behavior for payment management lives. So we, in the order processor, can't do that. We have to delegate that task to another party. We're asking the payment microservice to do that job for us in the same way as the warehouse manages stock. So for us to do our jobs, we are kind of coupled to that degree in as much as we have to have some degree of dependency on that functionality happening. So this is what I call domain coupling. So this order processor has domain coupling to the warehouse and the payment microservice. Now, the warehouse and the payment microservice don't use each other. They don't make use of each other's functionality. They're not even aware of each other. There is no domain coupling between those 2 things. So if I go and change how payments are created and maybe change the functionality or the interface that defines how payments are done by consumers, that could end up breaking functionality in the order processor, but it would have 0 effect on the warehouse microservice. So again, we can try and reduce domain coupling. There's still some things to watch for. Whenever you see a microservice that seems to have domain coupling on a load of other microservices, that can sometimes be the sign that that thing is doing too much. It's often also a sign of maybe an orchestrated process. Think like an order processor looks a lot like an orchestrator. An orchestrator is inherently, certainly as part of a BPM type solution or as an orchestrated workflow, will always have more domain coupling than other microservices. So it's when you see lots of outbound dependencies, it's not always something that has to be fixed, but it is something that's going to want a little bit more care and attention and a bit more observation, and go and investigate it. If I'm looking at an architecture, you always start looking for those boxes that have the most outward bound arrows and work out, is it doing too much? Maybe we should split it apart. So moving on from domain coupling, we've got kind of a different type of coupling called common coupling. And this is where we've got multiple microservices which are all making use of, say, a common data store, or this could be a common cache, or like this could be, we're all making use of, say, a common Redis cache, or even like a shared database. So in this example here, we're kind of managing the stock levels in this sort of externally addressable, publicly in terms of within our network perimeter, addressable stock levels. And the warehouse manages those stock levels, but basically is updating that in an externally addressable database. So here the order processor can come and read those stock levels from that data store. The forecasting service here, which is going to work out how many copies of, I don't know, Justin Bieber's greatest hits we should be buying, are going to be looking at those stock levels as well. Now, this is a stronger degree of coupling. The first is we're coupled on data, not behavior, really here. But with the big issue, the reason why this coupling is stronger and maybe therefore potentially more problematic is that a change to that common data store. So if we changed how stock levels were handled, we could end up having a breaking impact on a lot of the other microservices around us. And so this type of coupling is a little bit more worrisome. So this is common coupling. This is what happens when you have big, giant shared databases. And of course, that the degree of common coupling only increases as the complexity of the data increases. If we're just, say, coupled on a simple table that has the ID of the item and how many items are stock, that's a fairly simple and probably stable structure. But when it's a much more complex data model that we have coupling on, we're much more vulnerable to changes in that data structure. The simpler things are, the easier it is to maintain stability. So if you do have some degree of common coupling, a couple of things would be to make sure that that's as simple a data structure as possible, and that's less likely to cause problems. We could also potentially replace common coupling here with domain coupling. For example, we could say, well, that actually we're going to move stock levels to being an internal concern of the warehouse, and then the forecasting and order processor would have to go to the warehouse to ask for stock levels. By hiding that stock level management inside the warehouse, we allow the warehouse to implement information hiding about how stock levels are done. Whereas if we allow people to directly access a Redis cache or a database table, we haven't really hidden as much of that implementation detail as we might like. It's kind of the worst and most egregious form of coupling is called content coupling. And that's where one party is coupled to the internal implementation detail of another and the internal data of another. And the most common example of that is when we see things that are basically coupled to an internal database. So in this example here, I've got my shipping microservice. And ideally, when we think about a microservice, if a microservice needs to store data or state for some persistent, for persistent durable storage, then that should be hidden from the outside world. So in this example, the order processor is actually being well behaved. It's coming to the order microservice to request state changes, maybe in an order, saying, can you move order 123 from status placed to status fulfilled, for example? And the order microservice, when it receives that request, is able to say, okay, well, you've asked me to take I order 123, and you want it to go into state fulfilled. Well, it's currently in state placed. Going from state placed to state fulfilled, that's an allowable state transition. So yes, I'm happy for you to do that. And that's what we want, right? Because we want our code to control the allowable state transitions. By making this a whole big black box, we get to do that. And also, we don't need to worry exactly about how that data is stored or managed now. But then we've got a badly behaved participant here, the warehouse microservice. And the warehouse microservice somehow has been granted direct access to our database. So now we've completely bypassed information hiding. You can do some types of information hiding with direct database access. So some of the things you can do to sort of implement some form of information hiding include things like having restricted database accounts. So for example, you could do things like saying, okay, this account can only see these tables. That can help a bit. A better version of information hiding happening directly at a database tier would be to do something like using views. So I would create a dedicated schema, which is just a set of views onto this database, because then I can decide exactly what is exposed. So database views can help if you still want to do direct database access. But the big problem here is not necessarily the reads, but the writes. So what if the warehouse microservice is granted write access and is allowed to go and change the status of an order? So maybe it wants to be able to change the status of an order from state fulfilled to state shipped. Well, who decides if that's an allowable transition? Well, if I'm directly writing into this database, who decides what is an allowable transition is part of that functionality is in the warehouse and part of that functionality is in the order. So both the order microservice code and now the warehouse code both now has logic around how the same piece of state is allowed to be changed. That's an example of weak cohesion. Right? I've got kind of overlapping functionality. Now, hopefully, the logic or the state machine that we've created around how we manage these orders is the same in warehouse and order. But what if it isn't? We may now get warehouse making changes to state in a way which is actually invalid from the point of view of how order sees the world. And this is one of the big issues when you allow direct database access. It's not just that you're kind of being a lot more unclear as to what can be changed. It's actually you now can often get inconsistent behavior around how state is managed. And that's really, really problematic. There's a reason why this is also known as pathological coupling. This is the kind of the worst, most egregious form of coupling. So content coupling is really, really bad if you can directly write into someone's internal data state. It's better if you can do read-write, but should be avoided. If you can do read-only, it can be avoided. With databases, this can be somewhat alleviated using things like database views, but again, that's something to solve the read issues. If warehouse does actually need to update state in order, it should actually just do what the order processor does and goes to that well-defined service interface. And that would allow us to make sure that we've got a consistent set of code within order around the allowable state transitions of this particular record. This will make our code much simpler and easier to understand, much more error prone. It's reducing responsibility to the warehouse microservice, and once again gets us using domain coupling, which is much less problematic in terms of coupling of our system. So just to reiterate, we kind of got different types of coupling in microservice architecture. And there's always going to be some. We're trying to reduce it where possible. And if you see a lot of, say, domain coupling going on from one microservice, it might be cause for further investigation. But in general, when you're trying to make your systems more loosely coupled, you're going to be looking for stuff on the right side of this and trying to push it towards the left. And so sometimes by dragging things further towards the left, you can improve the situation. So sometimes you can make this better by improving the coupling, and sometimes you can make this better by improving the cohesion. They are both linked. Just to summarize, right, information hiding is super important. Yes, it's been around since the 1970s, doesn't mean it's wrong. I mean, we're not, I'm not wearing flares, but I am doing information hiding. It's a really simple idea, which I think too many people overlook. We are actually incredibly bad at doing information hiding within monolithic code, which is a problem. We should be better at that. But I think it's especially important when it comes to microservice architectures. A little simple tip for thinking about information hiding as a first-class consideration of your microservice architecture is never expose anything outside your microservice boundary unless someone asks for it. Start from that viewpoint. Think about what people want from the outside in, not the inside out. I see a lot of people violate information hiding when they do things like they don't actually talk to the consumers of their microservice. They just look at their data model and create an API that maps their data model. And that's sort of akin to having an object in an object-oriented system where you've said, oh, I'm doing encapsulation because all my fields are private, but then you put public getters and setters on it. That's not information hiding. That's not encapsulation. So never expose anything unless someone really, really wants it. That keeps your interface small. It makes it easier to maintain backwards compatibility. It also makes it much more explicit to you as a developer as to what parts of your system you can change safely. Information hiding is as much about being explicit about what is safe to change and what isn't safe to change. When it comes to coupling, some forms of coupling are worse than others, and where possible, you're going to try and limit it to domain coupling. Going via these well-defined service interfaces, it will clean up your dependencies, it will make your coupling a lot looser. But basically, all of these ideas together, they have as much value when it comes to building monolithic modular software as it does when it coming a microservice architecture. And if you're good at modular monoliths, you'll already be in a good place to build a microservice architecture. But microservices really have all the complexity of modular software and all the complexity of distributed systems. And this is also why I don't think microservices should be the default choice for people. Unfortunately, I think most people say, okay, I'm building a new system. Well, it's going to be microservices. And it's like, no, actually. Why? Right? My default position with microservices is I have to be convinced that microservices are a good idea before I'll do them. And that's how I work with my clients. That's how I work on the projects I build. And you don't have to listen to me, but I am the person that wrote all the books about it. So if you're thinking about microservices, great, but really think about modular architectures as much as anything. And if you can do modular architectures well, then you might be in a good place for microservices. And then all you've got to do is get your head around distributed systems. Anyway, if you want to know more information about anything I shared, you can go to my website. There are slides that are available for this talk are over at my website in the talk section. There's also information there about when the second edition of Building Microservices will be released and how you can read an early version of that. But we've got a bit of time. I think we've got about 10, 15 minutes. So I'm very happy to take any questions if anyone's got any. Let's stop sharing on my screen. So does anyone have any questions for me? You can unmute. You got three options at this point for asking me questions. So don't say I'm giving it. You could ask me questions on Slack. You can ask me questions on chat, on the WebEx, or you can just unmute yourself and use your human or robotic voice to ask me questions. I don't mind.
Sam, I have a question around schema checking. So I'm assuming schema checking applies to the client consuming the APIs as well as API to API communication.
I mean, I would start schema compatibility checking at build check-in time.
Yep.
Right. So if at runtime as a client, you find out the schema you're reading is incompatible with your ability to read it, it's already too late.
Yeah.
So you might want to do that as well to help you diagnose what's gone wrong in production. Like, this is just a wrong payload. Something's clearly gone wrong. But if you can do that schema compatibility checking, start the moment you check code in for your microservice. You can do, it's not an intensive activity. You're running a program across 2 text files and you're saying yes or no with lightning fast, and it can happen on your laptop even before you check in. So I'd start there.
Okay, thank you.
Cool. Had a question here from David via the chat. It feels like I'm on sort of like some sort of radio phone-in. So we've got David here on the texts, and he's in Berkshire. He's saying, do you see things like coupling, etc., as being different when we were talking about services triggering events to other services, e.g., expose a service bus topic style subscription? A really good question, David. Thanks for your call. So I think in a way, I find that event-driven architectures in general tend to be much more loose coupled, because the coupling goes from being between a service interface and another service interface, and it instead becomes towards an event. So as a microservice, if I emit an event, remember, events are really all about a shift in intent. When I emit an event, I'm not telling anybody to do something. I'm telling the world and anyone that cares, this thing has happened. It is up to other people to decide what they do. So from the point of view of emitting an event, the only kind of care I have from the point of view of the person emitting an event is that the event gets emitted and broadcast in the way that I want. Then the responsibilities are on the consumer side. So there, the coupling is not with my microservice. The coupling on the consumer side in an event-driven system is on the event that I have broadcast. If they only ever consume one of the 25 different events that I expose, they're only kind of coupled on one of those events. So for me, an event-driven architecture, when done with that kind of style of event-driven architecture, will inherently reduce the amount of coupling you've got. It then gives you all the pain and suffering of an event-driven architecture. I think it's worth it. I think event-driven systems are the best. But you know, it definitely helps around coupling. So I think it shifts that relationship. With request response-based systems, if I go and ask you to do something, I've got to know who you are. And if I'm calling an API, it can be harder to know exactly what parts of the API I'm using. So I think it's a little bit more inherently coupled, not necessarily in a bad way. I hope that kind of makes sense, David. Okay.
Nice.
Go ahead.
Sam.
Hi, Ian.
Yeah, first time caller, long time listener to your show. Do you think that the concerns around entity versus process style services are really just a kind of specialization of this problem? You know, that concern that basically people write services that are just CRUD based, right? And I think it's a specialization of that kind of coupling issue.
100%, yeah. I think and I think going back and looking at all this stuff and, you know, kind of reinforce that idea. And, you know, I always had a gut reaction against entity-based services, you know, the CRUD wrapper. And part of it was that whole, well, it's just like an object with private fields and public getters and setters. But it really does come back to this. Where is the behavior? Where is the logic? If I'm just, as an entity microservice, is just exposing APIs that just let you effectively get and set, well, the logic around how that is done is now spread amongst my consumers. Best case, I've got one consumer that might use those APIs. But that's not likely, right? Likely, I've got multiple consumers that are making use of it. And now the logic associated with how this state change is spread across all these consumers. And what's that? That's weak cohesion. What does weak cohesion give us, according to Constantines Law? Tight coupling. Yeah, so yeah, that for me, there's all these kind of things that you can pull apart. I think it's very difficult, though, when you sort of encounter that issue, say we're talking to a developer or an architect, you see that problem. I don't try and have the big conversation about coupling and cohesion, Constantines Law and stuff, because it's like they start yawning and you know, but you try and make it a bit more concrete. It's like, well, who makes a decision about what can change? What happens if you change how that stuff is done? And we talk about the cost of change, but absolutely, I think those are related. Okay, cool. Any other questions, thoughts?
Yes, Sam. So at what point do we start considering microservices then over just modularization of the code? Is there certain things that we need to consider, and what's your thought process on that?
My kind of the first question I always ask when I'm chatting to a new team about this, so we're doing microservices. It's like, well, why? Right? When you think about moving to a microservice architecture, there's got to be something wrong with your current architecture that you can't fix, and that you think microservices are going to address. So I always try and start with the outcome. What is the outcome that you're trying to achieve with your new style of architecture that you can't currently do with your current modular architecture? And for different teams, that might be different reasons. But so a team comes to me and says, oh, well, I want to move to microservices to kind of scale my application. I'm like, okay, great. Well, have you tried having 5 copies of your modular monolith behind a load balancer? Because that might help scale your application. And they say, well, we haven't tried that. I say, definitely try that first because that's way cheaper. So for me, I don't try and talk about the implementation detail. I say, what is the outcome that you need to achieve with this system architecture that your current modular architecture can't do? And then once you've defined what that outcome is, you focus any microservice migration based on that outcome. If your goal is scale and what you really want is a property to independently scale a part of your application, well, that is going to very strongly focus what microservices you create and what functionality you extract. If your driver, though, instead was, we are massively scaling up our delivery organization, we're spinning up more teams, we want them to be able to work in parallel, so we need ways that these teams can work without having to constantly coordinate, that might push you in a very, very different direction in terms of what your architecture looks like. And I think all too often, the outcome people are actually working towards is, I want microservices, not I want to change X, Y, Z. And if your only outcome is, we want microservices, well, it's easy to succeed. And it's easy for me to succeed because I sell books on the subject. But yeah, I always try and put it back to that outcome as a way of kind of keeping you honest. Because also, once you distill that down and get to, okay, this is your outcome, the next thing I'm going to talk to you about is, okay, well, if that's your outcome, let's think of the 10 different ways we could achieve that outcome. And oh, look, some of those things don't involve microservices and are way quicker and easier for us to try. Let's try some of that stuff instead.
Yeah. Okay. Okay.
Thanks. Okay. Who? Next question. Anyone else got a question for me? Yeah. All right. Well, look, if you do have any questions that you were too scared to ask on the line, you can put them in the track 6. I'm also just at Sam Newman on Twitter. I'm very easy to find. So just if you ask questions there, I tend to sort of retweet the answers so everyone gets the benefit of those responses. But I hope you enjoy the rest of the conference. And I'm sort of going to hang around for a bit more, see some more talks and things. So thank you so much for all your time. And I'll see you all again, maybe in the flesh in the future. So take care, everybody.